All right, and we're recording and ready to go. All right, I'm gonna start projectile motion with you guys today. You guys see, see what's gonna look like a projectile. It's got some questions. I'll take you guys over those, but before I get there, I got some starter things. All right, so okay, we do this. So I'm gonna flip my screen. Let's see, present screen to share. Okay, and then we start with the AP Classroom. So things I want to say about this. You guys know that there's a progress check that is up. It's a Unit 1 progress check, multiple choice that I want to cover next week. So have that ready by then. Okay. But I've also opened up a bunch of other sample problems if you want some extra materials to look at. So I've opened it up for the first 2 units. What have I got here? I got extra multiple choice questions. I've got extra free response questions. And actually last night I uploaded a few, there are actually 4 different types of FRQs that you'll see. One of them is experimental design. There's some other ones. They're either worth 7 points or 12 points is how it works. Right? And I went through, for Unit 1 and also for Unit 2, I found a pretty good example of each one of those types. So that you have a pretty good representative example. Right? So I want to do an FRQ with you guys soon, probably tomorrow I'm looking at. I've got it printed ready to go. But of course, we've only got so much class time. If you want extra problems, there's lots and lots of extra resources here. Also, while I'm here, go to course resources. You guys remember too, hey, look at all these videos, AP videos, they're all there. Take a look at some of those, and if you find them helpful, then you'll know. Like that. Okay. Right, you guys good there? Okay. All right, well, I've got the screen flipped over. I've got an animation for you guys. It's going to be a cannon, firing a cannonball. Right? This is what we're about to make sense of. Okay? So pay attention. Right? So cannon, blast a cannonball, boom. Right? See that orange? Hey, go back. See that orange velocity vector? That is a velocity vector, right? Right, so that could be like the blast speed of the cannon, right? But notice it's also pitched at some angle, right? And that's about to be important too. Now, to make sense of this motion, we're going to have to do this. We're going to have to break that motion into components, right? Now, here's why. Here's the reason. Because as the thing's flying through the air, and it's going to go into like a parabola shape probably, right? Make a parabola shape trajectory through the air, right? Because which way is gravity pulling? Down and only down. That's strictly vertical, isn't it? Right? Can you guys imagine for a moment? What if you turn gravity off? What would the motion look like? Yeah, it would just be a straight line into space. Maybe a crash on the moon, something like that. Right? That's if you turn gravity. So the fact that there's gravity, that's what causes it to bend down to parabola shape. But that only acts vertically. Right? So we're going to split this into components, and we're going to approach all these projectiles by looking either strictly what's going on horizontally or strictly what's going on vertically. Okay? And then we'll be able to put everything back together at the end. But the first step is always this, just split it into components. Okay? You guys can do sine and cosine. Right? Now, in my notes, I should I draw this a little bit different. I like to make little triangles. So the way I would do it is I would take this green component and slide it to the right, connect it tip to tail with this red component. Wouldn't that make a little right triangle right there? Yes. Right? That's the way I'm going to do it. Some textbooks do it this way. But let's watch the motion of this ball as it flies through the air. Okay, so components. Right. Now it's on the move. Ooh. Right? Looks like the cannonball was slowing down on the way up and speeding up coming down. That's looking if you focus on the orange. Okay. But that's instantaneously changing, and that's kind of tricky. But hey, what about those components, the green and red components? Right? Those are a lot easier to figure out in terms of linear motion. Let's start with the red one. Look at that v sub x. Now, that sub x refers to the x direction, right? Like horizontal direction. Right? Is that speeding up or slowing down to the right? No, because gravity's not pulling it left or right, and we've been ignoring air drag. So yeah, it has no reason to speed up or slow down to the right. It's just going to keep going to the right. Right? Versus, look at that green vector. It's going up really fast, then slower, and then it turns around and starts going down, then faster, picks up. Right? Who can tell me what's the rate that green vector changes? Yeah, 10 meters per second per passing second. Right? And then that orange vector, you could probably do what to put these back together? Use what theorem? Pythagorean, right? And that would finish it off. You guys see that? Right. So that's a roadmap of how to approach these type problems. Let me stop sharing screen, flip back over to this. Right. Also, we're back here. I printed out miniature versions of all the posters that I've been putting up in my room. So take a look at these real fast. So what I want to say about these triangles, these are obviously right triangles. They're actually similar triangles, so it's kind of like just take this and rotate it. Right? All these formulas, all 6 of these apply equally to both of these. So it's not like 3 and 3. No, all these apply to that and also to that. Same triangle, pretty much, right? And the one that I put on the right is also really could have helped you answer that last quiz question, right? Because if the weight pulls straight down, if there's like an incline that's sitting on, right, like you do, that actually, this is how much the weight would have pushed into the incline and pull along the incline. That's why I drew that triangle that way. Okay, so that's your trig. Some basic trig stuff. You guys navigate. You guys have a quiz on that. Right. We've been dropping balls off cliffs, looking at the graphs. Here's a table of values that goes with dropping a ball off the edge of a cliff. Okay. Then we've been throwing balls up, throwing balls down. Here's throwing it upward, the graphs. Here's some possible example numbers. Like if you threw up this fast, then all the numbers would play out that way. Okay. Oh, hey, you guys remember this? Hey, I'm going to pick up homework from you guys in a couple of days, but you know what? This deal's still on the table. So if you wanted to like start putting a YouTube channel together or something, send me the link. Then hey, I'll check that box. Okay. I'm working on your guys' quiz. I'll get that to you guys by the end of next week. But I'm working on that. That'll be a take-home quiz. Okay. Hey, it's the Three Amigos, and you know what? One thing that's nice about projectile motion is that I'm not actually going to give you guys any new formulas. We're still going to use these. No, we'll modify them a little bit, like say, you know, like the Y direction or something. But it's just going to be this, right? And then now we're getting up to, look at that. Doesn't that look like it's just begging to answer something about this? That looks a lot like that, doesn't it? Same thing, right? That's going to be the first step. Whatever the blast speed is, you just break it into components. This is how fast it's going across. This is how fast it's going up. You see that? Okay. Now, little detail that's really key here. Notice the subscripts on the V. V sub x, that's the velocity just in the horizontal direction. Right? That's the same all the way across. But look at the vertical direction. I didn't say V sub y. I said V not y. Right? That's the speed in the vertical direction initially. That's what the not is, right? Initially. Right? Because then, like 1 second later, of course, gravity's pulling down. This is going to immediately start slowing down vertically. Right? But it stays the same across. That's why it's just a solid x. Right? That's good. Right. Now, the poster I've got in class that's this, I did pencil in part of the trajectory. You guys see sort of like a gray pencil line on the poster hanging up there, right? Where the cannonball's going to deflect from this this green vector because gravity's pulling it down, right? And it's eventually going to go into a parabola shape, like an upside down parabola, right? And just the falling half could actually be represented by also this scenario where you perch a cannon on a cliff and aim it horizontally. The last few minutes of class, I'll solve this for you guys. Okay, right? But you guys see how this is a parabola with a vertex right at the top, right? Which could be like the second half of the story if you blasted it from the ground, and something like that. Right? Now, if you're up here in the blimp, watching the whole thing down happen beneath you, okay, it's going to look like the ball goes pretty much constant speed across, and that's what those blue ones are, right? Just mark it out. Right? If you take a picture every single second, see if they're equally spaced, distance equals speed times time. That's the only one that ever applies horizontally. It's not accelerating horizontally, right? But vertically, see how it's like, hey, it's like spreading out, right? That's your 1/2 GT squared, right? Because remember Paul Hewitt at the mine shaft? That's pretty much that equation you used to solve it, right? Just remember that? All right. So I think that's we're ready for this. Ready to go. Right. So suppose you did blast a cannonball 100 meters per second at a 53-degree angle from the horizontal. 53 degrees. I bet some of you guys are looking at that angle saying, I know where Griffin's going with this. Okay. So a few questions about this. First of all, what are the horizontal and vertical components? Right. That's going to be the first step, because to solve anything else, we've got to figure out what's going on strictly horizontally and vertically. Right. So I'm going to blow this up bigger. Okay. Cannon, blast in. Okay. It's going V blast 100 meters per second. Okay. This was at a 53-degree angle. Do this. Okay, so 53 degrees from the horizontal, should specify. Okay. This is V sub x. And trying to sort of keep the colors consistent with the posters. Okay. think of like blue and orange. That's pretty close to these. Okay. This is, I'm not going to call it Vy. I'm going to call it V naught Y. Okay, because of course gravity's pulling that direction or down, so I'll choose that one. Okay. Okay. You guys saw that in general, this is V blast times cosine of the angle from the horizontal. Okay. And of course, this would be V blast times sine of that angle from the horizontal. Okay. What I just wrote, you should feel really comfortable with that by this moment in the class, right? If you don't, then go back and solve some more trig. Right? If you plug in some numbers, plug in, say, 100 meters per second times cosine of 53 degrees. What's that equal to? 60 meters per second. Let's hold on to that number. That's going to be a really important number. Okay? And if you do 100 meters per second times sine of 53 degrees, what's that? 80 meters per second. Hey, I bet so many guys, as soon as you saw that 53-degree angle, you knew that this was going to turn out to be a what triangle? 3, 4, 5, 60, 80, 100. Doesn't that reduce to 3, 4, 5? Sure does. Okay. That's the first question answered. Okay. So now that we've got this components, we're free to move on and answer a bunch of other things. Like, for example, what's the maximum height the cannonball reaches? That sounds like a vertical or horizontal question. Vertical, right? And then what is the range? That's to say how far downfield does it go for it? Like lands on some camp down here. Maybe we're like lobbing cannonballs at some campsite. Cannonball. That sounds like a what kind of question? Horizontal. So we got a vertical question, a horizontal question, right? Start with the vertical. There's a reason actually I'm starting with vertical that you'll see as we go through this. Okay. All right. You guys good so far? Okay. Now, this picture, I'm going to draw in the path of the ball with this. I got a bunch of ink there. That's all right. That's where I do. Probably going to do something about like that, land way down here. Something like that. Path of the ball. Okay. And if I want to know something about maximum height, right? Well, all these kinematic problems, we've been going from some point A to some point B in this triple final. I have to identify those points. Now, this is going to be really critical for later on. Okay? We're going from the blast point, like from the mouth of the cannon. As soon as the cannonball leaves the cannon nozzle, it becomes in free fall, like right at that point. Okay? To maximum height would refer to this point right here, wouldn't it? That's max height. Okay? So let me label that. From here to here, I'll call that H max. Okay. Okay. Maximum height. Okay. And you guys know, of course, we're somehow playing off that 80 meters per second straight up. Okay. Do you think that the answer to this question, how high does the ball go, would also be the answer to the question if you threw a ball just straight up at 80 meters per second? Yeah, it's the exact same scenario, right? So whether you're blasting 100 meters per second at this angle, or if you just throw a ball straight up at 80 meters per second, they'll go to the same height. Okay? Okay. And that's the way we're going to approach this, the way we're going to solve this. Okay. Now, since you guys are AP, trying something new today. I think this is going to work. Is I want to solve this both in terms of variables, which is a skill you have to have, but also pop in the numbers as we go along so you guys can see that it's the same regardless of how you approach this. Right? So I'm going to make a couple of tax VB tables. I'll do variables and numbers, and of course they'll lead to the same solution. Okay? Tax VB, but I'm going to modify it because this is a vertical situation. So I'll call it T, well, do like A, Y instead of X. Okay? And I'll do V naught Y and VF Y. Okay? And I'll just double that over here so I can follow along with numbers. Okay. Okay. Now our numbers are going to be acceleration is in general it's g. I'm going to call up positive and down negative for this one, so I'll actually call it negative g. As you're going along with equations, just make sure that the signs make sense as you're plugging them in. But you can get that. We're solving for h max. Okay. We'd like to know what this is. What's h max? Okay. In general, have to just decide, wasn't V naught Y? Didn't that come from the blast speed times sine of that angle from the horizontal? Right? If I'm solving in terms of variables, that's what that is. Okay. And at the very top of the trajectory, that's my, a minute. Here it is. Okay. At the very top here, right? What's the vertical component of velocity at the very top? 0, 0. If you can recognize that, then you're gold. The rest of this is just going to fall into place. But you had to figure that out, right? Isn't it kind of moving up, 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 and then past that point it goes down, 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 right? Mm-hmm. Or if you threw a ball straight up, it's 0 at the very top, isn't it? Right? However you think about it. Okay. This number has to be 0. I'll even include that in the general case because I'm solving for H max. Okay? 0 meters per second. Okay? Now we do have some numbers with this. I'll call this negative 10 meters per second squared. Now this is still unknown H max, so let's call that. Right? V naught Y, you guys remember it came out to be 80 meters per second, and this of course would be 0 meters per second. Okay. Okay. So I'm gonna have general situation in terms of any variables, and then with the numbers that we got. Okay. Okay, so we're trying to figure out some kind of height, right? Bring in these guys. Which one looks like it's going to solve it for us? The first, second, or third? I hear you guys saying the third. I like that one too. Notice the third one does not mention time, and we're not asking for time yet. That'll be a later thing, and we don't know it yet either. Okay. Yeah, the third one is the fastest way to get it. As usual, there's multiple ways to solve this, but you guys picked a good one. So let's do it. Let's go. Final velocity in the y direction squared is equal to initial velocity in the y direction squared plus 2ay. Okay, that's pretty much that. Okay. I'm just going to copy paste that over here. Okay, and then plug in specific values. So I know that this whole thing's going to 0. For max height, that would be true. Right? I know that, okay, this one's kind of big. It's v blast times sine theta. That's all being squared. Right? And then it's plus 2 negative g times h max. Runs over a little bit, but that goes there, that goes there. This whole expression represents that. Okay. Let's get that. That's general. Maybe I should use a different E color for specific numbers. Like that. Okay. So this is going to be 0 meters per second, of course, again, okay. Squared, whatever. Okay. It comes from this number was 80. It's being squared plus 2 times negative 10 meters per second squared times h max, which we're solving for. Solving for h max. Guys good? Okay. So we got it in terms of variables. We got it in terms of the specific numbers for this example. Should tell us the same thing, right? All right, let me clean this up a bit. I've got a negative term here. I'm just going to add it over. So I'll have 2g h max is equal to, looks like v blast. Wow. Yeah. Times sine theta squared. Where that whole term's being squared, right? Okay. Versus over here, I got same idea. I'm going to just add this over. Got 20 with some units. H max is equal to now 80 squared. Looks like what, 6,400? Looks like that. Is that right?
Yes.
All right. Divide both sides. On the left side, I'm going to divide by 2g, and I'll get a general expression. H max is equal to yeah. I guess I could square both pieces, right? V blast squared times sine squared theta, all divided by 2g. Okay. This is a general solution. Okay. Then over here, if I divide this by 20, it gives me H max is, okay, the number is 320. The units, all the seconds cancel. One of the meters is left behind. Some number of meters, which is definitely good because meters measures height. So feels all right. You guys all right so far? Okay. Now, I want to check, does this general solution really give me this number? Remember the blast speed was 100 meters per second and it was at a 53-degree angle? You guys remember that? Okay. Moment of truth. We're about to find out if this stuff really works. So 100 meters per second being squared, multiplied by sine of 53.1 degrees, and I'm squaring that sine term, divide by 2 times, I've been using 10 for gravity, 10 meters per second squared, so, okay. All right, I just plugged it in. When I hit enter, what number has to show up on my screen? It better be 320. Let's see if it is. 319.7? I'll take it. Today's gonna be a good day. You guys good? All right, so AP, got to be able to solve in terms of variables. There were some other questions, though. Another question. So let's see where we are on our checklist. Okay. We broke that into components. Great. And then because we did that, we were able to figure out the maximum height. Okay. What's the range? How far does the cannonball go before it lands downfield? Yeah, I think I have a slightly better picture from my last class, so let me show you my notes from my last class. Right. It's the same idea though, right? Yes, yeah. Right. 60, 80, 100, boom. Right. We just solved for that. Right. And now I want to go from here to here. Right. I want to see how far does it go. Now, how far does it go? Can we just do distance equals speed times time? Using which speed? The 60 meters per second, because it's traveling that fast across. But for how much time? If only I knew how much time, I could very quickly figure that out, couldn't I? Yes. Yeah. How are we going to get time?
Well, the acceleration is going minus 10 every second, and we know it starts at 8. So
Yeah. Yeah. Oh, actually, so did you just solve it? So how many seconds?
16.
16. Yeah, you guys hear Ryan? Right. He's saying that it's going to come from your vertical information because it has to do with the fact that gravity's pulling down. Remember, we were saying if you turn gravity off, it would just fly into space forever, whatever, right? So definitely has something to do with gravity, something to do with vertical. We have to go back to this stuff. And you still get this 80 meters per second and say, well, if you tack every second goes 70, 60, 50, doesn't it take 8 seconds to reach the top? Another 8 seconds to reach the bottom? So Ryan just solved it already. But let's do it in terms of variables and whatnot, like I've been doing with you guys. Once you see this works. Also, I want to solve it in terms of that framework I've been giving you guys with the tax V table and whatnot. Okay. When you guys are solving AP problems, of course, nobody outside this classroom knows anything about tax GV, just you guys. You don't have to solve this way, but I think it's a pretty good framework, especially if you're not quite sure how to solve something. Okay. Gives you a good checklist. So let's go back to this. Okay. And we know some extra stuff now. Okay. So we know this. We have a whole expression now for HMAP. Okay, come back to that. Scratch that. Okay. This is still V sine theta, right? V blast sine theta. You know what? I'm going to use the same setup as we did before. Okay, but there's something important I gotta mention if that's going to be true. Okay. This came out to 80 meters per second. Okay. If this was 0, then this number came out to be 320 meters up, right? And then we have a whole expression for this, but I'm not going to take time to write it. Okay. You guys remember that? We're just looking at those. Now, if I plug in those particular numbers, you got to make sure that you know what you're looking at. Okay. Oh, guys, the setup that I just did. Yeah, whichever setup you're looking at. Am I going from the cannon to the very top or the cannon all the way down range? Only to the top. And you know that because see, Vy came out to 0. And also the height. came out to be like 320, right? That refers to this. See, if I go from the plane back to the plane, what's the height change? 0. So this y could be 0. You actually could solve it that way, but I'm going to solve it a different way. Right? And the way I'm going to solve it is I'm only going to go to the very top. But if I only go to the very top, doesn't that only represent half the hang time? This is a really good trick in this class. Sometimes you can take a problem, break it in half, and say, well, if I know half the hang time, I can solve for that using exactly these numbers. Then you can just take that and double it, right? So when you solve for t, make sure you know what t you're solving for. You're only solving to get to the top, which is half of what we're interested in. So I'm going to label it that way. I'm going to say that this is t sub half, right? Half the hang time. Right? We're solve that way. Right. So there's two ways you can go about this. There's a hard way and there's an easy way. You guys see this top formula? You could use this. If you use this, tell you two ways you go. If you go using exactly these numbers, isn't this going to become quadratic? And that would be really hard. Right? X in this case would be 320 meters. Right? That would be really hard. You could do it that way. Okay? Here's the second way you could do it. You could set x to 0, and that would represent y, right? Y is 0. And that actually would take you from beginning to end. You could solve it that way, skirt around quadratic. You actually would solve for the full hang time that way. You could do it that way. Okay? The way I'm going to do it is I'm actually going to use the second formula and play off these numbers and solve for half the hang time that way. Okay? So, yeah, multiple ways to solve this. If you like a different way, then go for it. But yeah, gotta give you some notes. So just go final velocity in the y direction is equal to initial velocity in the y direction minus gt. Okay. Vf y equals v naught y minus gt, something like that. Okay. Now, in general numbers, stick it right over here. Got goes to 0, coming from v blast sine theta minus g times and this really represents half the hang time, so I'll call it t sub half. Solve it that way. Or over here, also 0 meters per second equals it was a blast speed of 80 meters per second straight up in the air. 10 meters per second squared is being pulled down. And then again, only solving for half the total hang time. Okay. All right. You guys see a couple of algebra steps. I'm just going to take a term over and divide both sides by g. Right. So half the hang time is equal to v blast sine theta divided by g. Right. And therefore, wouldn't the full hang time just be 2 times that? Okay. So the hang time, the full time it's in the air is just 2 times that, which is 2 v blast sine theta, all divided by the gravity of the planet. Okay. So great. We have a general expression for how much time the cannonball is going to be in the air, right? The full hang time. Okay. Let's try it out with the numbers. This works out to 10 t half is equal to 80. With units, divide both sides by 10. Okay. T half comes out to be 8 seconds. Therefore, the full hang time, which must be twice that, must be 16 seconds. Okay. Exactly what Ryan was saying. Right? But I gave you guys a very formulaic way that you could never get it wrong. Okay? Is that? Let me check my general expression. I'm going to see if this actually works. 2 times the blast speed was 100 meters per second. The angle was 53 degrees. Divided by Earth gravity of 10 meters per second squared. This better come out to 16. Let's see if it does. 15.99. I'll take it. Physics works. And so now we know the total time. But remember why we wanted to solve the time. It's really a means to an end for us. Because we really want to answer the question, how far downrange does that cannonball go? What's not from here to here. We want to know from here to here. Right. How far? And to get that, we had to do speed times time for horizontal information. But we had to get time. Oh, well, we just got it. Is that? Right, so now we're ready to move on to actually answer the question. So distance equals speed times time. Notice I did a subscript x on the v to denote just the how far across. This is the hang time. We're looking at the full hang time. Okay. X equals vt. Either way. Okay. Now, in terms of a journal expression, this is getting pretty complicated because remember, v sub x was v blast times cosine of theta. That represents this right here. Right? And the hang time also was its own expression. It was 2 times v blast times sine theta all divided by g. Right, so that expression represents that. That's from continuing from your notes. Right. The numbers look a lot nicer. It's going 60 meters per second straight across, and it did that for 16 seconds. Boom, boom. Okay. So we can very quickly get the answer right here. This comes out to 960 meters. Okay. That's how far. Man, that's a long way. That's almost a kilometer, isn't it? Okay. But I can believe that because 100 meters per second, that's like over 200 miles an hour. Yeah. Yeah, okay, I can believe that's probably like almost a kilometer. That checks out. Okay. Now, what about this expression? Okay. Well, I'm going to clean this up a bit. Okay. I'll bring the 2 out in front. I've got v blast a couple of times, so I'm just going to square it. V blast squared. I've got a sine theta. I've got a cosine theta. And then all divided by g. Is that? Okay. Now, you guys ask guys an obscure trig question. And nobody's gotten this so far today, but I know I got a bright bunch in here. I wonder who's going to get this. Okay. You guys see that part I just circled in red? That's equivalent to something. It's not 1. It's a double angle formula. Who remembers double angles?
Wait.
2 sine theta cosine theta. That's the same thing as sine of 2 theta. Okay. So this is v blast squared times sine of twice the angle divided by g. Okay. Here's a general expression. Okay. It's a double angle formula. Okay. Well, here, I'll write that down here. So sine of 2 theta is the same thing as 2 sine theta cosine theta. Okay. This, by the way, has a name. What I just boxed in, this is called the range formula. Range formula. You guys see that you could choose any blast speed, pitch it at any angle, and for that matter, you could carry it around to any planet to figure out how far it's going to go. Okay? Let's see if this actually works. Let's put it to the test. V blast was 100, that's gain squared, times sine of, remember the angle is 53 degrees, so the 2 times, because double, 2 times 53.1 degrees, right? Then I'm going to divide that all by g, which is 10 meters per second squared. This number better come out to 960. Let's see if it does. 960.3. Oh, yeah. We are gold.
So why does the 2 sine theta cosine theta just turn to sine?
I forget why. I just remember that.
It just is.
I don't know.
You know what?
You're testing the limits of my knowledge.
I'll take it.
Yeah. That is the correct response.
It just is.
Is that? Oh, that's all the questions. We just answered them all.
We're done.
Yeah.
Let's go.
With that one.
Nap time.
No, wake up.
Nap time.
I got a new question for you guys.
Revolt.
You guys remember this? No mutiny. No. Back to your seat. You guys remember the page with the boxes that you picked up probably in the last couple of days? If you haven't gotten it yet, then there've been on the right side of your desk some page clip. Right. Has 6 different scenarios. These are all cannons firing cannonballs. Okay. And remember the pages with the boxes, they're really good for just some good fundamental questions, just working through the mechanics of how to solve these. So good place to start. I explicitly give you a bunch of numbers that normally don't get in textbook, but okay. All right, so the first scenario says this, and we'll draw this out and solve this whole thing by the end of class. A cannon fires a cannonball horizontally at some given blast velocity from the edge of a cliff. Hey, edge of a cliff. You guys know what's about to be happening. is, zoom out. Pretty much that right there. Isn't that going to be the picture I'm about to draw? I'm about to draw this, right? Cannon, cliff, blast horizontal, right? Okay, zoom in. Okay. The cannonball lands at some given horizontal displacement away from the base of the cliff. Okay, so we blasted this thing. We see exactly where it lands. Go out, measure how far did it land away. Can you find, then a series of questions, the time it takes to reach the ground, the height of the cliff? By the way, you need to answer number one to be able to answer number two. Okay. What's the vertical component of velocity, right? It's about to hit the ground, which is really one of a question that's a step to get to the last question that I care a lot more about. What's the total speed that the cannonball is striking the ground? Okay. In fact, we'll do total velocity. Right? Speed is just magnitude velocity. We'll also find direction. Okay. Now, what I want to say about this is, look at those boxes, those check boxes, how they are, right? Notice I gave you guys two separate tables. Right? So as you're trying to figure out what information do you have and what do you not have, right? I've got a 3-column table and a 5-column table. Which one of those tables do you think refers to vertical information? It's got to be the 5-column table because gravity is pulling vertically, so it's accelerating vertically. Versus the 3-column, that's a lot more simple math, isn't it? Isn't the 3-column just horizontal? Just x equals vt? That's the only formula we're ever going to apply projectiles. Horizontal, x equals vt, right? There's no acceleration. Right? Do you guys remember how many things you have to know vertically to solve it? 3. But if you pay close attention to the numbers I give you, well, you only have 2 things. You know gravity's pulling straight down, about 10 meters per second squared. The fact that you blast it straight horizontal means you also know v naught y is 0, because leaving the cannon, it's not going up or down. The cannonball is going straight. So it's 0 initial vertical velocity. Right? That's only 2 things though. Right? Now, how about horizontal information? Hey, I have 2 things here. Could I just do x equals vt and solve for t? Right? And see, what we're going to do is, all of these quantities are vector values except for which one? Which one's the scalar? Which one's the scalar? Time. Right? And you see, whether we analyze this thing vertically or horizontally to get from here to here, to get from the top to the bottom, whether we're looking at it going across or going down, doesn't it take the same time either way we analyze it? Yeah. So what I'm trying to get at is that time is the one variable that you are allowed to transfer across tables. Yeah, this is just a mut with. If it's helpful, then use it. If you can figure this out without the tables, that's great too, right? But all the vector values only apply in their direction of motion, either strictly vertically or strictly horizontally, right? Except for time. Whatever you get for time, you can transfer, right? And then you would have 3 pieces of information on the right side, wouldn't you? Right? That becomes solvable. Right? So again, this is just a framework. If you find it helpful, then great. And I'm going to use that framework actually to show you guys how to navigate a problem like this. Get picture going. I'm going to have, you guys know what the picture looks like. Anyway, cliff, cannon. Okay. Now this cannon is aimed straight horizontal. We got a blast speed. Okay. I'll call it v blast, except that v blast is also equivalent to vx in this case, isn't it? Because it's just straight horizontal. Right? That'll stay the same all the way throughout the trajectory. You guys see that looking parabola? That parabola? Okay. Maybe we fire a few cannonballs that keep landing in the same spot. Okay. So we might want to know how far does it land away? Actually, for this particular setup, I told you that was a given value. So x is a known value. I'm just going to make up my own numbers for the notes. Let's call this 500 meters. Let's say it lands 500 meters away. Okay? So keep going, boom, boom, boom. So yeah, it's landing 500 meters. Okay? And let's say we also happen to know the blast speed of the cannon. And maybe the blast speed of the cannon is the same as it was for the last one. It's the same cannon. I just hauled it to the top of this cliff. It can fire at 100 meters per second. Okay? There's that. Okay. one of the questions that's coming up is, can you use that information to figure out the height of the cliff? Maybe let's call it H. H for the height of the cliff, right? You guys think there's enough information lying around there? If you know gravity is 10 meters per second squared down to be able to solve something like that? Hopefully it feels like, yeah, I can see there's enough information lying around where I could figure that out. Right? And then later on, right at the tail end of the class, we're going to look at this cannonball that's crash landing right here. Right? I'll call this V crash. V crash. Okay? It's going to crash land, boom, on an angle like that, isn't it? Okay? But when it crash lands on an angle, isn't it moving a bit to the side and also a bit down at the same time? See like that? Doesn't that make a right triangle? I could call this V sub x. I can call this V final in the y direction, VFY. Right? V sub Fy. Right? Picture? Right? So we the last question we started with sine and cosine components, we split it up into components. But you see how this one's going to end, right? Is that it's probably going to end on a Pythagorean theorem if I put those components back together, right? You guys got it? Okay. Who's got questions so far? Okay. I think I'll even have time to address what this crash angle is.
So are we doing down equals positive?
Yeah, let's call it down positive because that would just give us all positive numbers, make that easy. Okay. Oh, and last thing I want to point out before I switch pages, look at this vector, this horizontal vector. Doesn't that say the same all the way across? Oh, right there. You see it's the same magnitude? Is that? So actually, we already know what this is. This is just 100 meters per second across. That one's easy. Okay. This one, well, we have to either know the time or the height of the cliff, which we don't know yet, but we can figure it out. Okay. It looks like we're going to start with horizontal information, aren't we? You know the horizontal speed, you know the horizontal distance. Can we just do x equals vt? Get it that way? Okay. All right. So I'm going to do the same thing I did before. Split the paper in half, solve it with variables, solve it with numbers. You guys see side by side, it's the same thing. Okay, go ahead. All right. Yeah. Okay. Okay. So we're going to have x equals vxt. Okay. I'll just copy paste that over here. Now, on the left side, I just want to solve in terms of variables, which means it's going to be the amount of time that it's in the air for is just how far did it go horizontally divided by the blast speed. Blast speed, Vx, I'll just use those interchangeably because, of course, they're the same thing. So that's just that. Okay. But in terms of numbers, I know this. I know it went 500 meters, and it was doing that at a rate of 100 meters per second. Divide 100 meters per second over. Is the time going to be 5 seconds? Okay. There you go. That's how much time it took for this exact scenario. From here to here, the only way to go that far at that blast speed is for 5 seconds. Okay. Well, doesn't that mean it was also falling for 5 seconds? Right? Now we're going to have enough vertical information to figure out things like the height of the cliff and the crash speed, right? Okay. Let me just continue notes down here. So now we're going to switch to vertical. Okay. So I can make a table, but if you know time and you're trying to figure out, let's do the height of the cliff. Guys, if you know time and you're trying to find the height of the cliff, which of these amigos is going to get there the fastest? First, second, or third? First, you know time, you want the height of the cliff. That's the only one that deals with both those things. Right? Seconds and meters. It's got to be the first one. Right? And you know what else, too? The fact that the cannon was aimed straight horizontal, V naught Y was 0. Remember the cannonball was not moving up or down coming out of the mouth of the cannon? So doesn't this term just go to 0? Right? Okay. So I can use a simplified form, which is what I'm about to write. I'm going to say it just boils down to this. 1/2 gt squared. Copy paste that over here. Okay. Let's get some values. I know h, the height of the cliff, is represented by y in that context. Okay. 1/2 g. Now t, isn't that actually this expression right here? Is actually that guy right there. So I should really go x on. All right, thanks. On v sub x, dn squared, like that. Maybe clean this up a bit. Right, so the height change would be, see, that's gravity multiplied by how far across squared divided by 2 times the blast speed squared. Okay. I think that should work, right? Well, we're going to find out. Okay. Let's try it in terms of numbers. Looks a lot prettier. The height of the cliff could be 1/2 times 10 meters per second squared for 5 seconds. Don't forget to square the 5 seconds. Okay. What's half times 10 times 5 squared? Hey, have we actually solved this before? How tall is that cliff? About 125 meters. How'd you know that?
Polish. Oh no.
Because it's been falling for 5 seconds. This is the Paul Hewitt mineshaft problem, isn't it? Oh, yeah, I saw it was going to happen when you saw 5 seconds. Like, 5 seconds. It's going to be 125 meters. I hope this expression comes out to 125. If I did it right, let's see. I got gravity 10 meters per second squared. It went 500 meters, so 500 squared. Okay. Divide by 2 times the blast speed was 100 meters per second, and square that number. Right. Please come out to 125. 125 meters. Look at that. Checks out. Okay. You guys good? Okay. So now we know the height of that cliff. Right? Guys good? Okay. We're getting real near the end here. Here's the last 3 things we're going to do. Okay. If I can figure out how fast it's going strictly vertically at the ground, that's one thing. Okay. Then I can take that in conjunction with how fast it crosses, do Pythagorean theorem, and get the crash speed. And then finally, we can go get that angle, maybe by doing some kind of inverse trig, right? Okay. That's how we're going to end class. So last steps. Right. Now, if you want to know how fast it's crash landing on the ground, I can go back to these guys. And I guess I could pick either the second or the third, but I'm looking at the second one, saying that's probably easier because I don't have to do square root. Okay. Probably saving me a little stuff. Okay. Let's do that. Same thing. Do this paper. Okay. Now we're going to be playing off this. Final velocity in the y direction equals initial velocity in the y direction plus at. Just copy paste that over here. Where we're doing, oh yeah, we're doing good. Of course, v naught y was 0. That's been the case all along, general or specific. Right. So here, just in terms of variables first. Vfy is see g for, that's where that came from. Okay. Multiplied by, now time we had a whole expression for, didn't we? No, where'd my time expression go? Oh, here it is. Right. Remember it was x divided by vx, right? So in terms of the measured known values, this is how far it went horizontally divided by the blast speed of the cannon, right? I think that's it. Vfy equals how far did it go times Earth gravity divided by the blast speed of the cannon. Okay. That should always tell you how fast it's crash landing. Okay. You can change cliffs, or sorry, yeah, you can change planets, you can change cannons, you can right, all the things. All right. How about in terms of numbers? Okay. Now I want to know Vfy. That's the goal. What is that? Okay. It's just 10 meters per second squared for 5 seconds. So this comes from here. This comes from here. You guys good? So doesn't that just have to be 50 meters per second? Okay. Now keep in mind that's Vf in the y direction. So that's not the total speed. That's strictly its vertical component. That's how fast it's going down. Let me check my work. Make sure I'm not lying to you guys. Okay, so this expression, if I feed in, remember what 500 meters across? Right? So if I feed in those numbers, 500 meters across, multiplied by 10 meters per second squared, divided by, the velocity of the cannon was 100 meters per second? Yep, 50 meters per second. Same thing. Right? Guys good? All right, so we are right near the end. We've got, I can pencil this in here. This is 50 meters per second straight down. Is that true? Right. Going in for the finish. Okay. As if you're going 100 meters per second across, 50 meters per second strictly down. Can you guys tell me the total crash speed? Like if you point a radar gun at it, right, it's about to hit the ground? It is Pythagorean. I'll just write right here. So square root of 100 meters per second squared plus 50 meters per second squared. Square root of all that. See what I get. There's a square root of 100 squared plus 50 squared. 112 meters per second. So that's that number. 112 meters per second. Now, interestingly, that's not a whole lot faster than the cannon actually blasted. Cannon blasted 100, and it's only picked up to 112 by the time it's, okay, kind of, well, it's going really fast vertically, but that's how Pythagorean theorem works. Okay? And last thing, what is that angle? Yeah, let's do,
Inverse tan.
I wonder if I can, yeah, it's definitely inverse tan. I wonder if I can make a general formula with this. Well, let's do the numbers first, and I'll see how much time I have. Okay. So that angle from the vertical, yep, you're right. It would be inverse tan of, it looks like 100 meters per second over 50 meters per second. If I'm playing off the two legs, that would be inverse tan. Okay. Inverse tan 150. Okay. That's 63 degrees from the vertical. Right? You have to specify an angle with respect to what? See, I'm doing it from the vertical. Right? Or you could do inverse tan. You could swap the two legs and do 50 over 100. And would that represent from the horizontal? Hey, the horizontal plus the vertical, those should add up to what? They should add up to 90. Let's see if it does. This is 27 degrees from the horizontal. Yep, they definitely add up to 90. From horizontal. Right. So there's two ways to describe the angle. Right. The way I've labeled it, the 63 degrees, that's from the vertical though. If you want to do from the horizontal, it's 27. They add up to 90. All good. Right. And okay, I'm not going to have time to do this in terms of variables, but you could solve for theta in terms of variables, couldn't you? I think you could. One of your textbook questions asks you pretty much that question. So try to hit that at some point. Okay. All right, now it's a wrap on class.